Now, if an object is both rotating and its center of mass is moving, then you have to consider both translational and rotational kinetic energy. So 1/2 mv squared plus 1/2 I omega squared, VCM is the velocity of the center of mass, and ICM is the moment of inertia around the center of mass. So what that means is that the object, so like say you've got a ball and it's rolling along the floor, well then it's moving, so it has a center of mass velocity, but then it's also rotating, so these given point on the ball is rotating. Those points are moving in an additional way, so you have to incorporate that. I want to make a note here that if you have a point mass going in a circle around some center point, you can treat it as either a 1/2 mv squared or a 1/2 I omega squared, but not both, because a point mass can't rotate. You can treat this revolution as a 1/2 mv squared or as a 1/2 I omega squared, but this point mass isn't spinning. If it's a point, it can't spin. So just keep that in mind. If you're considering a point mass, you don't use both of these terms. Now, if an object rolls without slipping, we can apply this relationship, and then our total kinetic energy becomes 1/2 mass times velocity squared plus 1/2 I times v over r squared. And then I'm going to do some algebra, a little bit of algebra with this. For whatever reason, typical way to factor this is 1/2 times v squared over r squared. And then what's left? Okay, well, r squared, that leaves us with mr squared over here plus I over here. For whatever reason, this is a typical way to factor this. So obviously, if an object is rotating, it has more total kinetic energy than if it's not rotating and moving at the same speed. But also, if an object has a given amount of kinetic energy and it is rotating, then it has more. Is going at a smaller speed because the speed is multiplied by this extra factor of I is added in there. So let's look at this. A hollow cylinder and solid cylinder of equal mass and radius are released at the top of an inclined plane at the same time. Energy loss is negligible as they roll without slipping. Which reaches the bottom first? Well, hollow cylinder, solid cylinder. What's going on here? What kind of energy do they have? Well, they both start out with some mgh. They're at the top of an incline and then they're rolling down. And that is turning into kinetic energy. So both of them wind up with this amount of kinetic energy at the bottom. So what's the difference? Well, for a hollow cylinder, we have mr squared. For a solid cylinder, we have 1/2 mr squared. So if we look at this formula, then we have the same amount of energy turning into 1/2 v squared over r squared times mr squared plus mr squared in one case, and for the hollow cylinder, and for the solid, we have 1/2 v squared over r squared mr squared plus 1/2 mr squared. So then we think about this, okay, and these are equal to each other. So then when we get along to this one, we wind up dividing out a bigger number because the coefficient here is 2, while this is only 3/2. So the hollow cylinder winds up with a greater velocity, which means that the hollow one is the one that reaches the bottom first. Let's take an example here. A solid sphere of mass 2.5 kilograms, radius 6.5 centimeters. released from rest and rolls without slipping 1.1 meters down an inclined plane, angled at 23 degrees above the horizontal. What is its speed? Well, solid sphere rolling without slipping. We've got, this is exactly the situation that just looked at in the previous example, just with numbers instead. So we want to know its speed, the speed of its center of mass. So we want to plug in, this is mv squared plus 1/2 I for a solid sphere that's 2/5 mr squared, and omega is v over r squared. So we notice what happens here. R cancels out, leaving us with mv squared, 1/2 plus, this is 1/5. So 1/2 plus 1/5, what is that? 5/10 plus 2/10, so that's 7/10 mv squared plus mgh naught. Mass cancels out. Sorry, I used a lowercase m in some places with capital M in other places. I meant the same thing. And then we can plug in numbers 9.8 and our height, 1.1 meters down an inclined plane angled at 23 degrees. Remember, this is 1.1 on the hypotenuse, 23 degrees. So then our height is 1.1 sine 23. And that's equal to 7/10 v squared. And then we can calculate 9.8 times 1.1 sine 23 times 10 over 7 square root. And we get that this is about 2.453 meters per second. Another example, so we got a block of mass m that slides through height h going down a frictionless ramp from rest. Ball of mass m rolls without slipping on the same situation, which takes more time. Well, for the block, there's no friction, so we just have mgh turning into 1/2 mv squared. For the ball, we have mgh turning into 1/2 mv squared plus 1/2 I omega squared. So all of the energy for the block goes into translational motion, while for the ball, the energy is split between translational motion and rotational motion. So, which takes more time? The ball takes more time. It has less energy going into translational energy. Now, this doesn't really correlate with your experience. If you do this with an actual ramp, the ball will make it down first every time, because real ramps are not frictionless. And when there is friction, then the block is losing energy to friction, while the ball is losing much less energy because rolling is more efficient than sliding. Say a block of mass m and speed v slides on a horizontal frictionless surface, then slides up a frictionless ramp. Cylinder rolls without slipping at the same speed, then up the ramp, which reaches a greater height. Well, for the block, we've got some 1/2 mv squared turning into mgh. For the cylinder, it's rolling, so we've got a 1/2 mv squared and a 1/2 I omega squared turning into mgh. And they have the same speed, these are the same. Cylinder has this extra term, so which reaches a greater height? The cylinder. It has more initial energy that is turning into potential energy. So it's going to wind up going higher. Anyway, so we have this new kind of energy, sort of, this 1/2 I omega squared rotational kinetic energy. We can apply energy conservation just like we would with other forms of energy, but now we have another term to our conservation of energy equation, that rotational kinetic energy.